I'm going to move this over here. So today we'll be taking a look at part 7 of 8 of our review series. That's right, this is the second to last. Hang on. No, this would be part 6 of 7. Oh, I think I updated that incorrectly. I'll fix the descriptions on these. This is oh, it didn't even change it. Really? Okay, well, it's thinking about it. Um, so this is part 6 of 8, but this is the 6th out of 7 units that will be covered. Uh, so our 8th installment of this series will be just reviewing everything. But this is our second to last chapter, and this is going to be simple harmonic motion. You might also know this as vibrational motion, and this is sort of the entryway into waves. Now, usually this would be also included on the test as mechanical waves and sound. They both make up an important part of physics, but those have actually been lifted this year from the AP Physics 1 curriculum. I believe those are getting kicked over to AP Physics 2 because they are important topics to cover. But it seems as far as we're going to go in here, will just be simple harmonic motion, which we'll see some wave-like behavior, but it's not going to be as in-depth as some of the future wave classes. I actually had, in my undergrad in physics, I had an entire class on harmonic motion. It was our classical physics class, basically spent the entire time. It got beyond simple harmonic motion. We got to complex harmonic motion, but this is a very useful model, being able to treat objects as masses on springs and seeing how we get these sort of restoring forces whose magnitudes are based on how far away they are from their original displacement. Yeah, so as usual, I will be having my chat up on the side here. I suppose let me also double check the audio levels on Twitch to make sure that those aren't going to be weirdly loud or anything like that. This looks pretty good. I can see all the pieces are up in place here. If I talk, do I hear myself talk? Well, the thing is lagging, so I can't really tell anyway. Okay. Audio looks good. I'm now going to mute that so we don't have any echoing artifacts. So yeah, I figured today we'll kind of go through our usual situation. We're going to spend a little bit longer going through the derivation of simple harmonic motion, and we'll delve a little bit into some calculus ideas. It's okay if you haven't taken a calculus class before. We're just going to touch these at the surface level, and these won't be tested. But it's nice to see them just to think about how where these ideas are coming from, just to build a nice intuition on what these equations mean. And then we'll again then just go through some multiple choice and a couple FRQs. We have less of each of those just because this is a very small unit. We can expect this unit to make anywhere from 2 to 4% of the test. Not very much. So maybe a couple problems like multiple choice problems and maybe like a part of an FRQ. And we'll see that in the FRQs that we'll be using other topics in earlier pieces of it, you know. Good. So to look at this generally, though, we want to start by, so to derive this motion, we want to think of a mass on a spring. This is going to be our model that we're going to go with. The other common type that we'll see is the pendulum, but that takes quite a bit of calculus to derive. This just takes a little. We'll touch on those a little bit, the definitions as we go. If you're having trouble following along, it's okay for these calculus parts. They're not going to be tested. But so we're going to imagine we have a mass on a spring on a frictionless surface. Now, is that in the right area? Okay, good. I want to make sure that these drawings we have are not going to be covered up by my face over here or any of our other lovely icons on our screen. And so we want to think about how this object is moving. And so our Ansatz are what we're looking for. Our Ansatz being German for approach. We're looking for a function of as a function of time, I want to be able to get a function where it will tell me my position at any given time. So I'm looking for some x of t. And so we know usually we can displace our spring from its resting position by some amount x, and that will induce a spring force. By Hooke's law, we can define this force as a negative k times x. Now, why do we include this negative? Well, the negative means that this is going to be in the opposite direction. So in this case, we have here, we're displacing it this way. So we're compressing it. That means the spring force is going to want to press in this opposite direction. So it's trying to resist this change and restore itself back to its original length. And then the same goes for if we were to stretch it. If we were to displace it to the right, the spring force would then pull left once again to restore itself back to its original spot. And then we'll assume we also have we know the mass of the object will be of mass m. And so we can relate these, we can relate this spring force. If we have no friction, this is the only force acting in the horizontal direction, so this will equal our mass times our acceleration. Now, this is where we get our first taste of calculus, and that's going to be to relate this displacement to our acceleration. For if you remember from our kinematics, we knew that the rate of change of position with respect to time was velocity, right? Velocity is how we change position. And then we can follow that relationship one step further and say the rate of change of velocity with respect to time is acceleration. And so in calculus, we call this relationship a derivative. If we take the derivative of position with respect to time, we get velocity. And if we take the derivative of velocity with respect to time, we get acceleration. And so we can treat this acceleration as the double derivative or second order derivative of our position with respect to time. So I can write this as a negative kx will equal my mass times the second derivative of x with respect to time. And so with respect to time, I'm going to write this as x double dot. It looks a little bit like an umlaut. You might also see this written as like a double prime notation, so it'll have two little apostrophes next to them. But if we want to get technical, the prime notation should be reserved for spatial derivatives, and this is a time derivative, a temporal derivative, if you will. So we prefer to use the dot notation here. And so we then know if we get this x double dot on its own, this gives us a condition on our function, because we have this x here and we're multiplying it by a negative k over m. So now I know I want a function whose second derivative is equal to the original function times a negative and times a scalar out front. And so for this first part, we want to think about functions we can use where the second derivative gives us a negative sign. So any calculus viewers at home might be able to have a little sit and have a little think about what functions satisfy this condition. If you haven't taken a calc class, perfectly fine. I'm going to spoil it a little bit for you because we know that sines and cosines will do this. So the short version, without going too gratuitous with the calculus here, but if we take the derivative of sine with respect to, so this is just sine of x, we take the derivative with respect to x, that's going to give us the cosine of x. And then if we take the derivative of cosine of x with respect to x, that's going to give us the negative sine of x. So sine fits one of these functions, and then cosine also fits one of these functions, because we can take this derivative again and pull that negative out front, and so we would see d dx of negative sine is negative the derivative of sine, which is going to equal a negative cosine. So we also see that cosine fulfills this requirement, because cosine, if we take the derivative of it once and twice, we get the negative of the original function again. Sine again, once and twice, get the negative of the original function. Cosine also, we take the derivative twice and get the original function. Now this gives us a sort of jumping off point. We know that we're expecting some sort of sine term in here, or cosine. For our purposes, though, we're just going to write sine for now. We'll show the other version with cosine once we get there. And so that's our first condition. We want the second derivative to be a negative, but we also wanted it to have this scalar modifier. So our square root of k over m is a scalar. This is not going to change with respect to x. As time changes, as our position changes, we expect our k value of the spring to stay constant, and the mass of our mass on the spring to also stay constant. So these two aren't changing with respect to either of our variables. Therefore, they're constants. And so this is then going to employ another trick of calculus. Again, if you haven't taken a calculus class, don't worry about this. But if you have, you might recognize the chain rule. And so now this is where we start to, where we want to think about what variables we're taking derivatives with respect to. We'll still do d dx because that's just kind of a nice standard here. But let's say I wanted to take the derivative of sine of a times x. We'll have some scalar variable a, take the derivative of it. And so what that is, due to chain rule, we technically have two functions operating on our variable, on x here. And so chain rule tells us we take the derivative of both working from the outside in, and we multiply them next to each other. So what that looks like is we first take the derivative of the sine piece. So that's going to give us the cosine of ax. So notice how we still have the same argument. And then we take the derivative of the inside, which is just a scalar multiplier timesing this, which is going to be multiplied by a. So we would write this as a cosine of ax. Which is pretty good here. Although we notice if we put k over m in our sine, so we want to be taking this derivative with respect to t, so we know that it's going to be something with respect to t there. And so our first thought might be, oh, well, let's put k over m here. And that seems pretty good, right? Because when I take the first derivative, I then get x dot of t, or our velocity term, would be the cosine with a k over m in front of k over m times t. But that actually wasn't our condition. We wanted the second derivative to have this. So if we take the derivative again, we then get our negative condition applies. We get a negative sign. We get a sine of k over m times t. But this scalar out front, we get another k over m because we have to chain rule this a second time. So we get k squared over m squared, which is really close to what we want, but it's just squaring it. So what we need to do for our scalar inside the argument is we need to take the square root of it. And so if we put the square root in here, this then gives us the square root of k over m. And then when we square that, that's the square root of k over m squared, which is just going to be k over m. Excuse me there. Let's put that in there. And so this term actually even has a special name. It's that important. We call this our omega. So it's like the curly W, which we're going to see again next time on rotational motion, but you might recognize it from angular velocity. And I hope you do, because there's actually some very useful parallels between that. And so this value is going to change based on what our simple harmonic operator is going to be. And that's going to be, for a mass on a spring, it's the square root of k over m. This is probably worth memorizing. You can derive it on your own each time, but there's a lot of problems we'll see where if we have this on hand, we'll just be able to solve them super easily. And so this makes a lot of our problems very quick. And then, yeah, for a pendulum, this would be g over L, the acceleration due to gravity divided by the length of the pendulum. This is also going to be an important one, probably worth memorizing, just because then it makes solving the multiple choices regarding these very quick. And we want to think about moving through the multiple choices at a good speed. We have just a couple things we want to add to our function just to fit all the conditions we want. First, we have to think about how sines and cosines behave. So if we take our let's get a set of coordinates here, and let's graph sine as a function of time here. And it's going to look kind of something like this. We're kind of going back and forth like in this oscillating motion, but we're actually only going between 1 and -1. That's our minimums and maximums for sine. But we want to make sure, we want to scale this to our actual distance that we're traveling. Because we can think about when we compress this, we've given it some amplitude. I guess we'd call this like a -a. And then once it moves back this way, it travels out to some +a. We would call this the amplitude. This is the maximum distances that this object is going to traverse. And because we're scaling it by factors of 1, we can just multiply this in front. So this looks pretty good. These are getting... Can we fit the a in there? Yeah, there we go. So that's not under the square root. I guess I'll try to make that a little clearer. But that looks pretty good. And then there's one last thing, and that's going to be setting our initial conditions. And so that basically means at time t equals 0, are we going to be starting at position 0, or are we going to be starting at a position A? And so we have two choices here. And one of them would be switching between the sine and the cosine. So if we look at the same graph down here, if we draw the cosine on this, we see the cosine starts at 1 and does the same behavior, but now we're starting at 1 instead of 0. So we can always say our initial condition would also be, I'm gonna get rid of these derivative terms here because we don't really need them. We only really care about the main functions, and that was only just to kind of show where we were deriving from. But we only really care about this guy. We're not going to need to know anything about the derivatives at this level. That's, again, just to show where these functions are coming from. So we could just set this as a times the cosine of, let's even be more general than this. Instead of writing k over m, we'll call this omega t. And I'll do that up here too. And for this case of mass on a spring, it is going to be the square root of k over m. But if we write this generally like this function now works also for a pendulum, or even for any other simple harmonic oscillator you could come up with. I know there's one you can do with capacitors, I believe in parallel with an inductor, I want to say. And many things can be modeled like a mass on a spring, but aren't quite a mass on a spring, such as in solid state physics when we have objects kind of being held in a lattice and then have them vibrating in place. Those are going to behave like masses on springs. And so, okay, so we still have this a sine omega t behavior. But so the other way we could change this, either by switching to cosines, or we could introduce what's called a phase angle, which basically says I'm going to add a term in my argument. We'll call this phi. And this term phi can either be 0 or pi over 2, because if I add this pi over 2 to this basically shifts my graph over. And so by shifting my graph over, that means this ostensibly makes this sine into a cosine. I believe there is a trig identity you can use to prove that, but we'll leave that as an exercise to the viewer. And then we can also write the same cosine version with a phase angle also, but notice that for the cosine, the phase angle behavior will flip. So for sine, we want, let's see, how do we want to write this? We want theta to equal 0 for x0 to equal 0. And I'm sorry, not theta, phi. And we want phi to equal pi over 2 for our initial position to equal a. And then for cosine, this flips. So for cosine, we want our phi to equal 0 when our x is equal to our amplitude, and we want our phi to equal pi over 2 when we want that x to go back to 0. Does that make sense? How we've got this kind of offset relation, and so basically we're translating our graph over, uh, and that's kind of this relation we're seeing here, right? If I shift this graph that way, I get a cosine graph. Um, cool, cool. Uh, yeah, I suppose that's more or less all I really want to touch on. Oh, I guess let's talk a little bit more about this omega first, too. Because we have, when we saw omega before, this was an angular, or I guess we're going to see this next time. Although you may have seen omega before, and when you saw omega before, we saw that it was an angular frequency. So this meant this would be the frequency that we could complete a complete circle. How many radians we travel per second. And so this radians per second we can treat like a distance per second, and for our velocity we said that was we travel one circumference per unit time. But in this case we travel just 2 pi radians per unit time. That's again the capital T for a period, the same period that we'll be using here. And this has the same behavior because the sines and cosines reset after 2 pi radians. Now this is not a coincidence because you can define the sine and cosine with the unit circle. Remember where we have our x and y, where our x is going to be equal to, let's see, so if we're adding an angle theta with that, our x is going to be adjacent, so our x coordinate will be the cosine value of our angle theta, and our y coordinate will be the sine value of our y of theta when our length is 1. And so then whatever height we're at is going to be that opposite divided by 1, which is our sine, opposite over hypotenuse, or our x value is going to be our x position, the adjacent side divided by 1, adjacent over hypotenuse, that's our cosine value. And so as we go through our thetas here, we can complete a full circle. That would be 2 pi radians. And when we complete 2 pi radians, the circle resets. That's the same thing of our wave coming back up to a spot that it originally was at. The distance between two equal points on the graph at any point, but there's going to be kind of a corresponding point some distance away, and this is going to be offset by 2 pi radians, or we can think of this as one period. So it's going to take us a time of capital T to travel back to that initial position. Okay, so kind of esoteric right now. A lot of this is a little overkill, but it's good for us to know where these are coming from. And we're going to see how these are used in our problems, which I guess let's jump to now. So, right off the bat, we've got a mass on a string, or mass m is attached to a horizontal massless spring with a spring constant k. It's set into simple harmonic motion. Its maximum displacement from its equilibrium position is a. What is the mass's speed as it passes through its equilibrium position? So we're already seeing some a's, some k over m's, and so we're seeing some pieces in play that we recognize from before, but we want to think about its speed. We're thinking, oh, well, that could be a derivative, but that might be kind of messy. There's a better way to do this. We can do this with conservation of energy. This is still going to be a simple harmonic problem, but the conservation of energy would tell us that at our maximum displacement, our mass isn't moving. We have all of our energy in potential energy of the spring. And then once that releases, it's going to accelerate it forwards until we pass the spot of equilibrium. And at that point, then every further distance we go is actually adding potential back into our spring, because our spring is now going to be trying to push a force back towards that equilibrium. So we know at that maximum displacement, all of our energy is in 1/2 kx squared. But our x, we're going to plug in a for, because A is that distance that we have for that maximum amplitude. Excuse me. And then when we come back through, once this moves, the point of maximum velocity is when we travel through the equilibrium, so our spring potential goes to 0, and all of our energy goes into kinetic. And so this relation that we have here will be able to solve for, what did we want? We wanted velocity, so we wanted speed, so magnitude of velocity. So we'll multiply both sides by 2, canceling these out. We'll divide both sides by m, so we'll have k over m times a squared is equal to v squared. And then to get velocity on its own, we'll take the square root of both sides. We have an a squared in here under the square root, which we can pull out, giving us a times the square root of k over m, which incidentally we can write as omega times a. This is going to be our definition of velocity that we can use. Another cool quirk of simple harmonic motion. But our actual answer we wanted to use was just this guy here. I figured that was nice to show just in case we'll need it later. But on the tests, this is what they were looking for. They were looking for answer A. Good. So 2 looks like kind of the same problem, actually. Mass m attached to a spring with constant k. If it's set into simple harmonic motion by a displacement d from the equilibrium, what would be its speed when it returns to equilibrium? Well, we just found that out. That's omega times a. Our omega is root k over m, and that amplitude, or the initial displacement in this case, was d. So d times square root of k over m, or d times our omega. Good, good. 3. Which of the following is true for a system consisting of a mass oscillating on the end of an ideal spring? The kinetic and potential energies are equal to each other at all times. That unfortunately is not going to be true, because we can come up with a time where the kinetic energy has all the energy and the potential energy is 0, and so those are unequal. Or we can come up with a time where the potential energy has all the energy and the kinetic energy has 0. Again, that means they are not equal to each other at all times. So we can rule out A. The kinetic and potential energies are both constant. That unfortunately is not true either, because we know these fluctuate as the mass changes its position. The maximum potential energy is achieved when the mass passes through the equilibrium position. That's not quite true. That's when the maximum kinetic energy occurs, but not potential. Potential is when we are the furthest from the equilibrium, when the spring is maximally stretched or maximally compressed. And I bumped into the mic there, but that's okay. And so that leaves us with D. But D looks like a good option anyway, because this tells us the maximum kinetic energy and the maximum potential energy are going to be equal, but they occur at different times. And that is true. That's actually the relation that we used up here to solve the first 2 problems. So D is going to be our best choice here. 4 and 5, we're looking at a block oscillating without friction on the end of a spring as shown here. The minimum and maximum length of the spring as it oscillates are respectively an x-min and an x-max. The graphs below can represent the quantities associated with the oscillation as functions of length of the spring. Okay, so which graph represents the total mechanical energy of the block spring system as a function of x? Now this one's a little tricky, because you might think, oh, well, our energy is going to change, right? We're losing potential energy as we go, but that energy is getting picked up by kinetic energy. We were told that this was frictionless, so that means there's no work pulling energy out of our system. So our total energy, the sum of our potential energy plus our kinetic energy, is going to be a constant. So D is our best choice for question 4 here. This shows a constant throughout our whole position here. But now, looking at 5, we just want to look at the kinetic energy, and this will change as we change positions here. We expect this to reach a maximum at the equilibrium and hit a minimum at the minimum, or at x-min and x-max. And so only 2 satisfy this. That would be B and C. The differences here are B are in straight lines, whereas C is a bit more of a curved line. So we want to think about how our kinetic energy changes with respect to x. And so we had it, our kinetic energy is really being fed from our potential energy, right? So we have, I don't really want to write this as equals because this looks a bit strange out of context. But so, okay, in context, we know this is relating to a 1/2 kx squared, right? So our, let's not write equals. We'll write inversely proportional to, I suppose. So proportional to the inverse. That's a true statement. So this means that as our x gets larger, our kinetic energy gets smaller, and then as our x gets small again, like the displacement, the magnitude gets larger, this also gets small. But as x goes to 0, our kinetic energy gets very, very large. And so we expect this to have a sort of x squared behavior that's nonlinear. That's going to be the curvy graph, so C is our best option here. Notice how we didn't actually need to delve into the mathematics too much there. Once we just got the qualitative look of how this is going to be like behave like an inverted x square graph, C kind of presented itself as a good choice here. Good, good. I guess we probably, okay, hang on. Even though, so that's the right answer, this is probably, there's a better way of expressing this. Would express this as the total mechanical energy minus 1/2 kx squared. This is a constant. There we go. So this, there was something fishy about setting it up before, because we also then, the way I wrote it before, it's like it looks kind of good, but we actually get an artifact at x equals 0, where that goes to infinity. We have a divide by 0 error, and that's not true. We don't have infinite kinetic energy, but we do have the case, in this case, this solves this better, because as our x goes to 0, our kinetic energy takes the entire energy. There's nothing being subtracted from our total energy. Good, good. Okay, so now looking at 6, any questions? Okay, looking good. Once again, I have my questions up here on the left, also just to kind of monitor the health of the stream to make sure it's not doing anything weird. But if you have any questions about anything I'm talking about or any of the problems that we see, feel free to type something into the chat. I'll be checking these periodically, and I'll try to engage with you, work on what you might find confusing, and hopefully we'll be able to find a better way to understand it together. So 6 tells us we have an object swings on the end of a cord as a simple pendulum with a period t. Another object oscillates up and down on a vertical string with a period t. If the masses of both objects are doubled, what are the new values for the periods? So this is going to be using that omega relation. We expect the omega for the pendulum to equal the square root of g over L, and for the mass on the spring to equal the square root of k over m. And so this tells us these are both going to be equal to 2 pi over t. And so we want to solve this for t. So in the case of the pendulum, we have t is equal to 2 pi over root g over L, which we could simplify a little, but I'm just going to leave like that. And in this case, we have t is equal to 2 pi over root k over m. Now we want to see what happens when the mass doubles. And so you might be able to tell from here, the pendulum isn't going to change because none of these terms depend on mass. And so that actually only leaves us one option. That leaves us with B. We might as well check the mass on the spring is correctly. So let's see what happens when we multiply this by 2. So we'll write a new version. We have 2 pi over root k over 2m. This is the same thing as writing root 2m on top times 2 pi over root k. Actually, how do we want to do that? Yeah, no, okay, so let's do that, but let's actually not do that with the m. We're just going to do that with the 2. And so we'll keep the k over m on the bottom. Yeah, there we go. And so now we show this term is equal to our original t. And so we see our new period is equal to root 2 times our old period, which is the option we had for B. So B is our best choice there. Any questions on how we did that? You guys are great listeners. Cool, cool. Next, we're jumping ahead in problems a little bit. Again, it's kind of hard to find problems for these because this is a very difficult subject to broach without getting too calculus heavy too quickly. And so we're going to see this makes a small portion of the test. And so, like I said earlier, there's not going to be as many problems for this. We've got a block on a horizontal frictionless plane is attached to a spring as shown above, and it oscillates between an A and a negative A. It has simple harmonic motion of amplitude A is how they state this. So which of the following statements about the block is correct? At x equals 0, its acceleration is maximum. That's not going to be correct because that would mean the force is at a minimum. But we still believe the force accelerating this is Hooke's law. So that's going to be a negative k over x, and that's going to equal mass times acceleration. If x goes to 0, this goes to 0, meaning our acceleration at the center is 0. And that should make sense because that's our point of maximum velocity. At x equals a, its displacement is maximum. That is true. Let's just double check all our other ones to make sure they're false. At x equals a, its velocity is a maximum. That is not true because that would be at a minimum. And at x equals a, its acceleration is 0. That's also not true. At a, our acceleration would equal negative k over m times our displacement. That's non-zero. So yeah, B is our best choice here. 22. Which of the following statements about energy is correct? The potential energy of the spring at a minimum is x equals 0. That is true. The potential energy hits a minimum at x equals 0. The potential energy of the spring hits a maximum at x equals a. That's not true. Oh, sorry, that hits a minimum at x equals a. It's not true. Kinetic energy of the block hits a minimum at x equals 0. Nope, that's when the kinetic energy maxes out. And then the next one is kinetic energy maxes out at x equals a. No, that's when the kinetic energy hits its minimum. So a lot of these are just kind of looking at different, when we have different maximums and minimums. These are kind of qualitative problems, which really we can just derive with conservation of energy. Thinking about taking potential energy, our 1/2 kx squared, and converting it into kinetic energy. And it's all about our displacement from that origin. 23. A simple pendulum consists of a 1 kilogram brass bob on a string about 1 meter long. It has a period of 2 seconds. The pendulum would have a period of 1 second if the string were replaced by 1/4 of the length. String replaced by 1 twice the length. The bob were replaced by a mass quarter the length. The bob were replaced by 1 4 times the length. So we expect, again, the frequency of this guy to be the root g over L. So we can intrinsically rule out C and D because we know the period of this is not going to depend on the mass of the bob. This is kind of an important thing for pendulums here. This was actually the original way they defined a meter in metric. It used to be the length it would take to get a pendulum to oscillate at a frequency of, I believe it was 2 seconds, was the original one. But again, this problem is then not consistent with that, but I do believe the original was 2 seconds. Turns out we now define our meter more cohesively with the speed of light, and that's because our g changes wherever you measure it. If you change your latitude on Earth, where you're going to measure your pendulum, you're going to get subtle variations in g. And so if you're using that to define what a meter is going to be different based on the country you're in, which is not very good for a metric. But so we can compare this to 2 pi over t, and we want to double this. So we know that's going to increase. Okay, so yeah, so we want to reduce this by a factor of 2. So this is going to be like dividing it by 2. We introduce a 2 here, so we'd want to introduce 1 over 2 here, which would be the same thing as introducing a 1 over 4 here. So we would want 4 times the length? No, that's not. A fourth of the length. No, we would want twice the length. Hang on. Okay, so let's try a different approach. I didn't really like that one. I managed to confuse myself there. Okay, let's do what we did before, where we start by, so that's going to equal 2 pi over t. Then we'll get t is equal to 2 pi over root g over L. Okay, that looks good. And now we want to double t. So we're looking at a case where we have this is equal to 2 times the original. So 2 times 2 pi over root g over L. That means this root g over L has to be, if the 2 pi stays the same, this has to be half the magnitude. If this needs to be half the magnitude, our length needs to double. No, our length needs to quadruple. Because it would be 1 over 4. 23 is actually not an accurate question. It should be 4 meters long. I think the answer they're looking for is 2, but I think they forgot about the square root. I'm actually going to double check because I do have an answer key with this. And I didn't want to use this, but I believe that they're making, unless they're taking a really different approach that I'm not missing, this is not going to be the same thing. A quarter of the length equals half the period. Oh, okay. So, okay, I see what they did. Okay, so they did. So let's start from up here. And they write this then as 2 pi times the square root of L over G. And so we want to reduce this by 2, so we have to reduce this by a factor of 4. Okay. Okay, so I was just getting turned around. So I made the mistake. I apologize. I was getting turned around by the number of flipping fractions. So it's not B. It is actually A. If we want our period to be... I also got the periods the wrong way around. I thought that we were trying to half, or trying to double the period, but we're trying to half the period. So then if we were halving it, yeah, that would make sense. We would then want a quarter of the length, and then that would spin twice as quickly. Again, because of this square root, we see if we have square root of 4, or this would be like L over 4, that gives us a 1/2 out front. Good. All right. Cool. So 24, a pendulum with a period of 1 second of Earth, where the acceleration of gravity is g, is taken to another planet, where its period is 2 seconds. The acceleration due to gravity on the other, the acceleration due to gravity on the other planet is most nearly what? Yeah, I guess let's start from this spot again. From 2 pi is equal to root L over G. So if our period doubles, we expect this to shrink by a factor of, no, our period, okay, so our period doubles, so we expect this to get smaller. We want a smaller denominator by a factor of 4, because then the square root of 4 is 2. That gives us a g over 2 under here, multiplying this by 2 on the top. This is a 1 over 1 over 2. Okay, so g over 4 would be our acceleration, giving us twice the period. That's what we expect, yes. Good. 25, an ideal massless spring is fixed to the wall at one end, as shown above, and a block of mass m is attached to the other end. of the spring, which oscillates at some amplitude A on a frictionless horizontal surface. The maximum speed of the block is Vm. The force constant of the spring, I'm guessing that's the K value they mean. The spring well, yeah, let's assume that's the K, because that's the only thing that we aren't given. I usually heard that a spring constant, but force constant makes sense, because it lets us translate displacement into force. Yeah, and so that's going to show up through conservation of energy. Again, we expect 1/2 Ka squared, our maximum displacement, our maximum amplitude, to have all of our energy and potential energy equal to the point when all of our energy goes into kinetic energy, and that's that Vm squared. Oh, and I guess we want the big M because it's a massive big M. Doesn't really matter, but that's okay. Yeah, and so we can multiply both sides by 2, but now we want to get the A squared over there, giving us K is equal to M times Vm squared over A squared. And that's going to be option D. Good. Cool. I think that was our last multiple choice. I told you this was going to be a short one. Here we go. Let me grab a quick drink of water. You guys can take a quick peek at this, see if you see what you guys are thinking, how you'd want to approach this, and then we'll take a look at it together. All right, so we've got a block of mass m is resting on a horizontal frictionless table and is attached as shown to a relaxed spring of constant k. Second block of max m and some initial speed v naught collides with it and sticks to the first block. Develop expressions for the following quantities in terms of m, k, and v naught. So we know this is going to be an inelastic collision, so we can't use conservation of kinetic energy here, unfortunately. But that does mean we can use conservation of momentum, which we saw last time. So our momentum at the beginning of the system is just going to be our mass of 2m traveling at a velocity v naught. Our mass of 1m isn't moving, so it's not contributing any momentum. But after the collision, we see both masses moving together, so with a combined mass, will travel at some velocity v naught. Oh, not v naught, v final. Which we'll just call V because that's what they're looking for. Yeah, and so let's bring that back to here. And so that gives us then 2m V naught over 3m, which is just 2m plus m, is equal to V. And so the m's cancel, giving us our V is equal to 2/3 of that initial velocity. Good. X, we want to find the maximum distance the spring is compressed. So this is then going to be the maximum kinetic energy we hit, right? At this point, we're displacing this from an equilibrium, and so this is the point of maximum kinetic energy, where we have our mass, which is the 3m, because they're all together, traveling at a velocity of 2/3 v naught. And to get the kinetic energy, we'll square that. And then that's going to equal 1/2 times k times our maximum displacement, x. And that's going to be the furthest this travels before we lose all that kinetic energy. It's all in potential, and then it's going to swing us backwards. So we'll multiply both sides by 2, and solve for x, so we'll divide by k, and take the square root. So that gives us... So we'll have 3m over k is equal to, or times 2/3 v naught squared is equal to x squared, not v squared, excuse me, which we'll say is equal then to, we'll take the square root of everything, but we're gonna, that was not meant to be a 2, that was meant to be a 3. It's equal to the square root of this guy times just this on the outside, because we'll use this to undo the square operation. That little square up in there. Good. And so, yep, and that's the square root of that. Good. So we get x is equal to root 3m over k times 2/3 v naught. Good. And that is all in terms of m, k, and v naught. So that's what we're looking for. Awesome. C, we want to find t, the period of subsequent simple harmonic motion. Well, that's pretty easy because we know how our omega behaves. We know the square root of k over m, our m being 3m now, because it's 3 times that initial mass, is equal to our angular frequency, 2 pi over t, giving us t is equal to either 2 pi over square root of k over root 3m, or 2 pi times root 3m over k. Either or works. Yeah, I mean, I'm just going to leave it like that there. So we've got both options. Very nice. Any questions on how we did that? Looks pretty good. All right, so now we have a slightly more complex one going on here. We have an ideal spring of unstretched length 2 meters is placed horizontally on a frictionless table as shown above. One end of the spring is fixed, and the other end is attached to a block of mass m at 8 kilograms. The 8 kilogram block is also attached to a massless string that passes over a small frictionless pulley. A block of mass m, 4 kilograms, hangs from the other end of the string. When the string block system is in equilibrium, the length of the spring is 0.25 meters, and the 4 kilogram block is 0.7 meters above the floor. So, on the figures below, we want to draw our free body diagram. So let's start with our big mass. We have gravity. We always have gravity acting on us. Yeah, pretty much always, unless we're in like vacuum, like with absolutely nothing else around, but kind of an unlikely scenario. We have a normal force. Because we're sitting on the surface, we have the strength of the force pushing us upwards. We have a tension force from the string, and we have a spring force from the spring. So we'll label these as such: Fs, Fn, Fg for gravity, and Ft for tension. S is for spring, N is for normal, tension, gravity. Good, good. Yeah, and then for this guy, it's a little simpler. We've only got 2 forces. We have that tension force pulling us upwards. This is going to be the same tension force as below because the pulley was massless, so that makes these two bound together, which makes them third law pairs. And then we have the force of gravity. So that is then going to be Ft is equal to Fg. Cool. And so we're in equilibrium. So that tells us we want to find the tension in the spring. And this is pretty easy because we're in equilibrium, we can use the Newton's second law for the second mass, telling us the tension minus its gravity force is going to equal its mass times acceleration. But we know if we're in equilibrium, this acceleration goes to 0. So that just tells us that our force of tension is equal to our mass times gravity, which is just going to be 4 kilograms times 9.8 meters per second squared, which is 39.2, I believe. Yeah, I don't need to calculate that. You will have a calculator on the test, so don't be shy to use a calculator, but I've done this enough times where I've actually seen that calculation that I remember it now. So that's nice. Yeah, and so this gives us, although I made a mistake here, this is not in meters per second squared, because technically it should have also been kilograms. Kilograms times meters per second squared is newtons. So that looks better. Next, we want to find the force constant of the spring. And this is pretty good because now we know the tension. And if we're again at equilibrium, we expect the spring force to equal the tension force. So that would look like Ft minus Ff equals big M times A. But once again, our acceleration goes to 0. So we get our tension force, which we just calculated, is equal to our spring force. So that tells us this is equal to our k times x. The negative is just to tell us the direction, but this is going to give us the magnitude. And this k is what we're looking for. So we'll take 39.2 newtons and divide it by our x, and that displacement was 0.25 meters. So this is the same thing as multiplying it by 4, and that I do want a calculator for. We're going to take 39.2 times 4, and I get 156.8. And that is going to be newtons per meter. That is the units of a spring constant. And so now we cut the string at point P. So that drops this block on the bottom. We got to calculate the time it takes for it to hit the floor. And then that also sets this top block into simple harmonic motion, which we want to calculate the frequency and then the maximum speed. So let's start with the time taken. That should be pretty simple. How do we want to do that, I guess? So I guess we can look at this in the y direction. We are traveling a distance. We want our y of t to equal 1/2 gt squared. We are traveling a distance of 0.7 meters at a rate of 9.8 meters per second squared for some t squared. We want to get t on its own, so we'll multiply by 2, divide by 9.8, take the square root, giving us t is equal to the root of 2 times 0.7 over 9.8, 4 over 9.8. So this is square root of 1.4 over 9.8. I get a time of 0.377 seconds, or the square root of 1/7. Yeah, so that's about what we'd expect too, but like a third of a second. It's not going to take it very long to just kind of drop down there. Good, good. Any questions so far? Looks good. Let's get a little note down there just to get our answer. Calculate the frequency of oscillation for the 8 kilogram block. Well, we know our K value now. This was our K value down here, right? So this tells us our frequency of oscillation, that's going to be this omega, right? So, well, yes. Technically this is our angular frequency, so we can technically divide this by 2 pi. Do they want us to divide by 2 pi? I guess they... I mean, I probably wouldn't usually, but I think they do want us to in this case, because this would then put it in terms of, instead of radians per second, this is just going to be oscillations per second, which makes sense for frequency of oscillation. How frequently do we oscillate? So yeah. So omega is going to equal 2 pi times that frequency. So our frequency is just this omega over 2 pi. And we know our omega is root k over m over 2 pi to get us our frequency. And that's going to be, let's see, 156.8 over our mass, which is 8, all under the square root, all over 2 pi. Let's try this out. So we want 156.8 divided by 8 divided by 2 pi. Oh, did that, okay, no, that kind of screwed it up, didn't it? Because that I divided by 2 and then multiplied by pi. It didn't combine them. Oh, and now my calculator's gone. Oh, it's all gone wrong, friends. That's okay. We'll make this work. There we go. That's much better. So we see our frequency ends up as a 0.704. And our units for this would be either 1 over seconds, or we use hertz. Hertz is 1 over seconds. Yeah, that's our frequency of oscillation. So we complete a full oscillation every 0.7 seconds. No, sorry. We complete 0.7 of an oscillation every 1 second. So it takes a little bit more than a second to complete an oscillation. And then we want to calculate the maximum speed attained by this block. I mean, we can jump ahead because we got the equation before this was equal to, oh, I guess we'll derive it. It's not that big a deal. We don't know our amplitude. Oh no, we do. We totally do. Because, yeah, so once again we have this 1/2 kx squared is equal to 1/2 mv squared. Now I was a little bit confused because I was like, well, we're not going to have an x. We don't know our amplitude of this. We do, because when we cut the point P, that is our max amplitude when we stretch the string at 0.25 meters. So we multiply this by 2, bring the m over. This gives us v is equal to root k over m times x, or times that amplitude. This is another way of saying omega times x, or omega times our amplitude, which was that equation we saw before. And in this case, that's then going to be, we've got 156.8 divided by 8. And then we're going to multiply this by 0.25 meters. So should be on the small side. 156.8 divided by 8 under the square root times 0.25. It's about, well, it's exactly 1.106. Okay, well, it's about that because it's a radical. And that's going to be in meters per second. No, let's see if we can fit these all down here nicely, just so we get a nice filled out board here. That's in hertz. Make sure for your final answers you're including units. That is something they can dock you for. There we go, in meters per second for our velocity. Cool, cool. And with that, I think that was our last problem. That is indeed. So, like I mentioned, this is going to be a shorter unit here. We can expect this to make up anywhere from 2 to 4% of the test. Not a big topic, but this is worth learning because these are really useful ideas, especially if you plan on taking physics in college, which I would highly recommend. There's a lot of things, too, that we can use the simple model of a mass on a spring to model much more complex things going on. This even gets used in field theories later, if you're ever interested in using the word quantum field theory and like actually knowing what it means instead of just using it as some sort of sci-fi term. Well, so thank you everybody for stopping by. Thank you for watching. On Sunday, we have our last unit. It's going to be the torque and rotational motion. That is on the 2nd. That'll be Sunday at 5 p.m. Pacific time. And then after that, we'll have our last one will be on the Tuesday. That'll be Tuesday night before the AP test on Wednesday. And that will just be reviewing everything. Follow us on Instagram. We'll keep you posted about when these streams are happening, and then upcoming projects and fun stuff we'll be doing. And you can also check us out at 314education.com. We've got some extra resources. We're trying to grow that site a bit more. And if you're interested in doing any tutoring, I offer remote tutoring sessions that you can access through 314education. Yeah, and if you want to get caught up on all our previous videos here, you can look at our Twitch and YouTube channel has all of our previous streams archived. So you can watch whichever unit you're missing to help review those trouble spots. Well, thank you everybody for tuning in. It's been a slice. And until the next time, you guys take care, keep safe, and I will see you guys on Sunday.